All right, so today I'm planning to finish the Connect 4 programming problem example, which is similar to the tic-tac-toe problem that some of you are probably still working on. But before I start that, are there any questions about the final or anything else that you want to ask? Okay. Yeah.
How long will the final be?
The final is an hour and 50 minutes. It starts at 12 o'clock in this room on Wednesday. 1 hour and 50 minutes. So it looks like an exam, but has some extra problems on it. Okay, it's just a big exam.
You said it mostly covers 3 and 2.
No, all three, one, 2, and 3, those exams, plus sorting. So you need to know sorting. I'm asking sorting. I'm telling you right now, there's a problem with sorting. So you have to produce some code to do sorting. Binary search is on there. Linear search is probably on there. There'll be a problem that asks for you to implement a class. You know, like the fraction class we had on the exam 2. Might be similar to that, or the school bus class, or the egg carton class. All of those are possible, the type of problem that I might ask. Okay. So let's continue with Connect 4. Oh, we need to let's remember how that works. I think this was it. There it is right there. So the player goes, and then the computer goes. We'll make the computer take a random play. And after, what we'll do when we code this up, you know, we have a 2-dimensional array that represents these slots. So each slot is in one of 3 states. Either it's empty, or it has a player piece in it, or a computer opponent piece in it. So 3 possible states. And in our code, we're representing the state of being empty with a dot. And if the cell has a dot in it, it means the cell is open. If the cell has an X in it, that means the player has taken that cell. If the cell has a 0 in it, or an O, I think, an O in it, like tic-tac-toe, then that means the computer has taken that slot. And you'll see that we have a 2-dimensional array of char, so that's a character. It doesn't contain an int or a string. It contains a character, it's an array of single characters. And single characters are represented with these using apostrophes, not quotes. A quote looks like this. It's got two marks on it. So the apostrophe is used to mark or symbolize a character. So the character is in between the 2 apostrophes. So here we have a period. So we have the board, which is 6 rows and 7 columns. You'll see there's 6 rows and 7 columns. So it maps directly to what we see visually here. Now, what we'll do is, because this is a graphical user interface here, what we look at on this website, but we have a text interface. We have a character interface. So when we run it, what we do is display the state of the board, which is all periods in the beginning. And then we prompt the user to choose a column. I'll choose column 0. And then after we choose column 0, then we render the board showing that we made that move. And then we let the computer take a move, and then we render the board again showing our move and the computer's move, and then we prompt for the next play. But of course the computer is not taking a move yet, so we need to add that. Let's do that. Let's do that next. Control C to break. So what we're doing to simplify the problem, we're breaking it into functions. And this is what you need to do for the tic-tac-toe problem. So here's a function that simply initializes the board. This would be called once at the beginning of the program. And so I look down at main. We call init board right there, see? So initialize the board. So there's a loop within a loop, a nested loop, setting the value of every cell to a period. Then here we have another function which displays the board. So every time there's a move, when something happens, the player makes a move, the computer makes a move, we want to redisplay the board. So we put that in a function here. So we tuck it away. It makes it easy to think about. So it's a loop within a loop, right? For each row, we print the element at column 0 through 7. And because the board is storing characters, we can send the characters directly into cout, into the standard output stream. So it's convenient to use characters. Otherwise, if we use numbers like 0, 1, and 2, we could do that. But then we'd have to have an if condition here. So if 0, then print a dot. Else if 1, then print an X. Else if 2, print an O. So we could do that. That's not a big deal. A Boolean value is not good enough. The board, we can't have a board. We can't have a two-dimensional array of bool. Because bool only has 2 possible states, true or false. But we need to represent 3 states for each cell. It's either empty, taken by the player, or taken by the computer. Anyway, here's the function to display the board. Here's the function that prompts the user to pick a column, because that's how you play. When you play, you select a column. So you type in a column number. We prompt the user for a column number. And then if it's legal, we only want to accept a legal column number. So that's why we have this loop. We sit in an infinite loop, and we break from the loop when we get a legal move from the user. And so when the user enters in a column number, we store it in picked column. That would be a column index. And so we look at the very top cell of the column. If the column is free, if the column is not filled up, then the top cell will be empty. You should have a dot in it in our data structure. So if it does have a dot in it, that means picked column is a good number. So we break from this input loop. Now we're not checking other things. If the user enters in column 11, that'll break things. But we're not checking. We can add that. We can add that check, okay? And if we want to do that, we'll do that today. Otherwise, we'll just gloss over that detail, and won't do that today. But we have one check. One check is that the column that the column that the user picked is not filled up yet. And so after we get a good column number stored in picked column, then we start at the bottom, row equals 5. We start at the bottom of the two-dimensional array, and then we work our way up from the bottom in the picked column index, the picked column index. And R represents the row. So we start R at 5, which is the bottom. So when we play the piece, it should slide all the way down to and occupy the lowest possible location that it can. Now here, this is 0, 0 for us. So this is row 0, row 1, row 2, row 3, row 4, row 5 here. So we start at row 5, and we say, look, does row 5 have a dot in it, and is it empty? If it is, then we're going to place it in row 5. And if it doesn't have a dot in it, has an O or an X in it, then let's look at row 4 and place it in there. And so that's why we have this loop that starts with R equaling 5, and we go backwards until R is greater than or equal to 0. We still do the loop. When R is 0, we still do the loop. But when R is less than 0, then we exit. We need to decrement R rather than increment R. So here it is. If in this loop, if we find a blank space in this line here, then we write our X into that spot, and then we're done. We break. So that's the player moves. Now look at the main loop. Video games, they have this thing called a main loop, it's called the game loop or the simulation loop. And this thing normally, like in a real-time game, like a game that you might play, right? Like whatever. That this main loop runs a lot, 30 times a second, 60 times a second. That's like your frame rate, right, in a game. And so this is called a simulation loop. But for us, we have a loop as well, but it's not for generating very sophisticated graphics. So it's kind of like turn-based. When we take a turn or the opponent takes a turn, we recompute. So we make this an infinite loop. We display the board. First, the computer takes a move, and then we display the board. And then we check to see if the computer wins or if there's a tie. And if there's a win or a tie, we'll break the loop, and we're done. Then we'll have the player take a move, and we've already implemented that. And then we check, and then we display the board to sort of visually show that move taken. And then we repeat the check, except we're checking now for the player winning. And so we have this implemented. We have this implemented. We need to implement this check, and the computer taking a move. All right, let's do this one. The computer takes a move. We just call the function computer moves. Because here we call this one player moves, so it's similar. I'll do it up here. Let's see, player moves, computer moves. So when this gets called, we know that there's something available. We won't call this if the board is full of moves. We won't call this because we'll have checked to see if there was a winner first. So what are we going to do? Well, there's a couple of ways to do this. We could scan across the columns and make a note of which columns are not full, and then randomly select from that collection. That's a little complicated. We can do that. It's cumbersome. It's efficient. Another way to do it, which is not as efficient, although it doesn't matter in this problem, is to randomly pick a column, just like player moves. we randomly pick a column, and we sit in this infinite loop. So in here, we randomly pick a column, and if it's got an empty slot in the top, then we're done. But if it doesn't, then we randomly pick another column. So we just keep picking until we hit it. So there's only 7 columns. So we're going to hit it, in less than a millisecond. So, I mean, why not do it, right? So we'll do it that way. And then the logic is the same as player moves. But it's a little sloppy. It relies on, the random number generator has to, generate all the values nicely for us. But I think it's reasonable. It'll run. We won't notice it being slow, that's for sure. I'm going to copy those lines. Just paste them right there. So now here, we don't need to prompt we don't need to prompt the computer to pick a column. We're just we're the computer. We're going to pick it now. Loop until rand selects a playable column, something like that. Loop until we select a playable column. Maybe select is not the right word. Generate. Yeah, it's important. See, I'm taking some pains here to get the language precise, right? Because it's easier to maintain your program. That's something you need to get in the habit of. Keep things clean and organized. Make sure your comments are precise. The language is precise. Variable names should be meaningful. Loop until we generate a playable column. So this is the spot right here where we don't read it in from a human user. We get it from that rand function. But rand gives us a random integer between 0 and some max integer value. So what do we do to squeeze it into the range 0 to 7 or 0 to 6? You need to know this for the final. Rand returns an integer. It could be 1,000,000, right? It could be a big, normally it's a big number. But what we want integers that are between 0 and 6. That's 7 columns, by the way, 0 to 6, right? So how do I transform what rand returns?
And modulus 7.
That's it, modulus 7. You got to know this. That's the trick. We've seen this many times already in this class, and it's even been on the exam. So that's how we generate a random integer between and including 0 to 6. So there's our column. And this logic that we carried over is pretty much the same, see? And then with this logic is all the same. Actually, we can look for a way. See, there's a lot of duplicate here. This is different, but this is the same here, isn't it? So what we could do is we could extract this, because see, this code is duplication. And so it's not good to have duplicates of code in the program. Let's look at how we can sort of factor out the common functionality and put it in a function that both of these functions call. But before we do that, let's see if our logic is correct. Well, look at that. The computer, is playing an X. So it needs to be an O, right? So this should be an O. So it's a little less identical now, less identical. It's no longer identical, it's just similar, because this line of code here, my mouse. There it is. This line of code here is slightly different from this line of code. And of course, this line of code here is different from this line of code. There's only two lines of code that are different. Of course, we don't need the prompt is also another difference. So we could say, well, they're small enough functions that we don't have to worry about duplicating the logic. So we could just leave them as they are. So maybe we'll save that task for the end if we want to kind of refactor that later on. But let's solve the problem first. All right, let's do this again. So I'll pick 0, and now I'll pick 5. Looks like it's working. It's working nicely. Yeah, see, it's in that loop there, so I can go to there. Look, can't take that one anymore. So that's working. So we've got we have computer moves, display board, and player moves. Now what we need to do is check for the computer win or tie and the player wins or ties. We'll do it like this. Check. We'll do it like this. How about, I'm going to think it out here. If it's a tie, then see out tie and break. So we're going to check for a tie here. And then after checking for a tie, if we don't break because it's a tie, oh, actually we need to check. I want to check if it's a win first. If the computer wins, the computer wins. This is a tie. So I want to check to see if the computer wins first, because that'll simplify the tie. Because the tie, if we check the tie first, the computer may win on the last move. But if we don't write the tie routine, if the tie doesn't look for that, the tie routine doesn't look for that, we'll declare it a tie. So we need to check to see if the computer wins first. If the computer doesn't win, and then all the cells are taken, then it's a tie. All right, so let's implement these. Let's do tie, that's the easiest one. How are we going to implement tie? So remember, when we call tie, we know that the computer has not won, and we know that the player has not won. So how can we check to see whether there's a tie or not? How would you do that? Anybody want to take a guess? What check? Anybody want to suggest a solution there? How do you check for, what's the algorithm that we need to run to determine whether there's a tie? This is assuming we know that the computer hasn't won. We know that there are not 4 O's in a row, and we know that there are not 4 X's in a row. So that's a precondition. So we know that we don't have to check for that. We just have to check to see that the thing is filled. How do we check to see if it's filled? Well, we don't only care about the top row because things fall down, right? So we'll just have a loop that checks the top row. So, oops. So we have the loop, and we're going to, the top row is r equals 0, so we're going to range across the column. So I'll use C. And it has to be less than 7. There's only 7 columns. And this is just like the problems we've been working on. What do we do here? If something, then return something. This is just like the problems we've been working on. So dots, right? If we find a dot, what do we do?
False.
They return false. So if board of column C, what row? Well, 0. So board 0C, so we're all in row 0, going across the top. If the value stored there is a dot, then it's not a tie because it's not filled up, so we return false. If it goes through that loop and we don't end up returning false, it means there was no dot in the top row, so we must return true, there is a tie. You can test that, but we need computer wins. We're going to stub out the computer wins function, just so that we get compilation. Here we go. Ah, it's broken. Oh, that's because the user went. That's because the user went. So we have to change the test here. I should have, after the player moves, we need to check for the player win. And then I'll see, because the player moved, it was a tie. So this didn't get to run. You know, instead, I went to computer moves, but there was no valid move, so it's an infinite loop. See? So I never got down to here. So let's do the this business if the player wins. So if the player wins, then player wins and we break, and then we check for the tie. That should be good enough to test it. And there's our complete loop right there, by the way. That's the end. We don't have to modify main anymore, I think. We just have to stub out these functions and then implement them. So this would be player wins. All right, now we're testing the tie function. Well, that row 5 is unlucky. So here my last play. So when I enter this in, it should say tie and terminate the program. We did it. We got it. Okay, so the tie function is tested at this point. Now we just need to implement computer wins and player wins. We're really close to the solution. So we need 4 in a row. And we also need to look for diagonals, right? So a diagonal wins. So this, yeah, that's a diagonal right there. So we have to check for the diagonals. So 4 horizontally, 4 vertically, and 4 in a diagonal. So this is probably the most cumbersome part of the program. And you know, that's a lot of code to check for this. So I know in advance I don't want to repeat that code between these 2 functions. So I'm going to write a helper function. And I'm going to call it wins, and it's going to take a char. And I'll call that char the, what is it, the, what's a good, I don't know a good name for it. You know, I'll call it Z. Think about a better name. Maybe peace. How about that? No, let's do Z. Or character, opponent. What's the name of something that's in a game? The opponent, the player. What's the word that includes both of them? The participant? We'll leave it at Z for now. So, or we'll call it the symbol. That's easy. Symbol. So if wins O, then return false. Else return true. Then it's the opposite down here.
You spelled return wrong.
Okay, I'll fix that. Thank you. Thank you for pointing that out. This is return. So now there's a lot of logic, checking the diagonals, the horizontals, the verticals. We don't want to repeat that between these 2 functions. So we wrote a function to include the common functionality, to execute the common functionality for us. And we just pass in some little bit of data to distinguish between the 2 cases. And by the way, this line is can be simplified. That's what that's better than this. That would be typical. You know, you would see that. This is equivalent and much simpler, right? If wins is true, I say, oh, wins X. That shouldn't be returned false, right? That should be returned true. So I had this wrong to begin with. So if wins returns true for X, then the player wins. We return true for player wins. You know, if wins returns true for 0, then we want to return true in this function. If wins returns false for wins O, then we want to return false for this as well. So these are simple one-liners right there. Okay, here we go. So the first thing we're going to do is we're going to check the horizontals. Check the horizontals, I'll say it like that. And then we'll check the verticals. And then we'll check the diagonals. So there, we're putting comments in there. how do we check the horizontals? And we have the symbol. It's either an X or an O. It's a net variable. I want to find 4 in a row. Now now look here. So we're just going to say, forget about the bigger problem. We just cut it down to a smaller piece. Now we're just going to focus on how do we see if we can find 4 of something, 4 symbols, whatever that is, X or O, in a row, in a horizontal position. Well, think about it. We're going to do exhaustive search. We're going to do it like this. We'll do 1 row at a time. So in row 0, we're going to see if there's an X or an O in column position 0, 1, 2, 3, or column position 1, 2, 3, 4, or column position 2, 3, 4, 5, or column position 3, 4, 5, 6. You see that? We just do that for column 0, and then we do it again for all the for row 0, and then we just do it for all the rows. So we're going to need we'll need a loop, a big loop which goes through all the rows. So for integer r equals 0, r is less than 7, no 6, plus r. Now we can type it out just the way I read it, because there's not very many positions to check. Or it could have a loop that runs 4 times. You want to do it? You want to write out all 4 positions, or do you want to have a loop that runs through the 4 checks? Loop or no loop? Loop? So the column will start at, well, where would it start? This would be the start position, so it's not exactly the column. Yeah, this is we'll say it's the start column. So we'll say it's C. We have to do it like this. So this is the start position. C equals 0, and I had to think about that one for a minute. For C equals 0, C is less than 7, plus C. We're still going to need, now actually we have to have this loop. Let's see, how are we going to do this? So these are actually start positions. So I'm going to call it start. I'll do start column. So the start columns go from 0 to, what was it, 4? No, 3. 0, 1, 2, 3. The last start column that we want to check is 3. So this is less than 4. So 3 is less than 4. 4 is not less than 4, so we stop at 4. And once we have a start column, then we want to check for 4 of these guys. So this is like a differential. It's the offset from the start column. And I'll call it offset. So if the board of something, how are we going to do this? is it equals or is it not equals? And what goes there? And then we return something, right? At the end, we're going to end up we need to see if there's 4 in a row. I got it. I see. We can't do it like that. I can't explain this slowly. I think I'm going to just have to type it out. This is where we're going to check 4 things. We're going to check 4 things to see if the 4 things equal the symbol. Where the symbol is going to be either an X or an O. So it's the current row that we're in, and the start column plus this offset. If that equals the symbol we're looking for, then we're sort of good, right? This is a good thing. I'll put it like this. So this is good. That means keep trying. But if we find something that is not working, let's do it like this. If it's not a symbol, then it's bad, and we'll break something. How are we going to do this? So let's start off. So we have we're going to go through, I'll use a Boolean variable. And we'll call it win. And I'm just going to guess. I'm going to say it's false. Right? Maybe I'll change that to true. So the win is false. No, I'll say win is true. Take that back. Win is true. And so we're going to assume that we're a winner. And so we start with the offset 0. And if we find something that's not the symbol, then win is false. And if we get to the, of course we can break. I'm going to simplify this. And if we complete that loop, and win is true, then we found one, right? It's got to be an easier way to do this. I'm starting with win equals true. If we found, starting at the start column, and if I run through 4 offsets, if I find one that's not the symbol, then I'm going to say, no, win is false. Let's break. But I think there's a way to do this without this. How can we do this without this variable? Is there a way to do it without that variable? Or maybe it's simpler. Maybe it's simpler if I do it like this. The win is false. No, that won't work. I'm going to leave it like that. I think that works. Actually, we have some nest. We have a loop and another loop. So it's a little complicated. So I took your suggestion to use a loop for that. But there's another way we could have done it. Let's look at the other way. Let's look at the other way. Let's suppose we don't have this offset. let's get rid of the offset. If board, and I'm going to call this, I'm just going to call that C now. If board of RC equals symbol and board of RC column plus 1 equals symbol, and you see where I'm headed here? Let's suppose that we find 4 of those symbols in a row starting at C. Then we have a win. Otherwise, we don't do anything. Look at this. These two pieces of logic are equivalent. Which one's easier to read? The second one? Wasn't it obvious? To me, it's the second one. So using that loop, which was our first thought, we had to introduce this temporary variable, and it started to get messy with, triple nested loop in there. But we're only looking for 4 in a row, so why not just do it like this? So much easier to look at. And I'm just going to clean it up a little here, just to make it fully symmetric. Look at that. It's even easier to read. So I'm going to kill this code here. I don't think this is, and this code, by the way, this is refactoring. This is very important when you're writing a program, you're developing systems, and you do this as a job, day in and day out, you're doing this. Well, you're going to want to like to do this, by the way, and it is fun, I want to tell you. That you're going to always think about how to simplify your work. You're always looking for ways to reorganize and keep it as clean and clear as possible. So that's what we did today. All right, this checks the horizontals. Let's check the verticals. But in fact, what we can do is, we're pretty close to the end here, by the way. We could even, control may reach the end of a non-void function. So we have to return a false at the very bottom here. Let's see if we can get 4 in a row. Oops, I messed it up. Am I going to get a horizontal? No. Maybe that's too hard to get. I didn't do a good job there. Let's do a better job. 0, 1, 2, 3. I'm going to hope for a horizontal. There we go. Look at that. Horizontal check worked right there. Computer wins. All right, now let's check the verticals. And we're going to use, I'm sure it's similar to this. So we're just going to start by copying that chunk of code there. We're almost done. Just finish, check the verticals, check the diagonals, we're done. That's the end. We've whittled it down to this. So let's check the verticals now. Now look, I'm just going to use my intuition here. And it's not a big stretch to use your intuition. We need to go the other way. We're going to replace rows with columns and columns with rows. Let's do it the brain dead way and see if and then we can check the logic afterwards. So I'm going to make this a column, make that a column, make that a column. And of course the columns, there's 7 of them, so I'm going to change that to 7, okay? Let's make this a row. Make this a row. Keep the 4 at 4 because we need 4 in a row. And the row, be r plus 0, r plus 1, r plus 2, r plus 3. Oops. And oops. Yeah, I'm just guessing. I'm just guessing that that's going to work. Do you think that would work? Probably, right? So the columns. So we're gonna range across the columns here, 0 to 6. We want to check slots, 0, 1, 2, and 3, 1, 2, 3, and 4, and 2, 3, 4, and 5. So is that right? That's 5, 4, 3, and 2. So this should be, this is not a 4. I made it wrong there, right? See that? Check that. That should be a 3. That wasn't the 4. That 4 didn't represent 4 in a row. It represented the last column that we could select. Now it's going to represent the last row we can select. So we had a bug in there. So we had, see how I did that? We did it by guessing first, and then we went and checked the logic mentally, and we caught a bug. I think we can test that one. So we want to test the vertical. And I'm going to do it like this. I'll make it a 3. 0, 1, 0, 1, 2. Now make it a 2. Player wins, so we got it. Now we check the diagonals. How many diagonals are there? Well, there's 1, 2, 3, 4 here. How are we going to check the diagonals? We're going to enumerate all possible diagonals, or we're going to use loops. So maybe we're going to do the diagonals in 2 steps, something like that. Like I can start on the diagonals that start in a column position. So all the diagonals that start in column 1. So 1, 2, 3, 4. And then I go to the next column, 1, 2, 3, 4. Then I go to the next column, 1, 2, 3, 4. Then I go to the next column, 1, is it this one? 1, 2, 3, 4. So we want to stop at this column 3. So those are all the columns that we want to check, starting in the first row. And then in this, we do the same thing for the second row and the third row. And in the third row, we would stop here. And there's nothing below the third row that could give us a diagonal that has 4 in it. So I think we can do it. The code is going to be very similar to what we already have. Let's go across the rows. We'll do it like this. 1. So we're going to start in row 0, and we're going to go down to row 2. This is 0, 1, 2. Because row 2, I can get a diagonal of 4 here, and I can't go below row 2. So the row will start at 0 and terminate at row 3. We don't check row 3, we only check row 2. And the columns, oh, I see, these are the diagonals that slope to the right. Now we need the diagonals that slope to the left. That's the problem. Okay, we're only getting the ones that slope to the right. So the columns go from, well, it's the same, it's 0 to 4. And the check is going to look like this. And I'm guessing here, okay? I'm sure that this is, well, I think this is going to be close. Because we need a diagonal. That means we need to add this offset to both indices. Does that make sense? That gets a diagonal, doesn't it? 0, 0, 1, 1, 2, 2. So you have to add the offset to both row and column indices. Think that works? This is check the right sloping. Check the right sloping diagonals. Now we have to check the left sloping diagonals. So the left sloping, it's going to be similar here. We're going to go, the rows are the same, right, because we're going to go down. But the columns need to start here and end here, see, because we can get 1, 2, 3, 4 like that. And we can go across, all of these are good. So this is 0, 1, 2, 3. So we have to start in column 3. And then we just go down to column 4, and this is the last left sloping diagonals. This is the last row that has valid left sloping diagonals, row 3. So this is 0, 1, 2, 3. So this is column 3. And the row starts at 0 and goes to 3. It's the same thing. But the column starts at 3 and goes to 6. 3, 4, 5, 6. It's 4 columns. But what do we do here? Anybody know? This is the end. I predict once we fix this one last thing, the whole program runs. These are going to be left sloping. So the columns, whatever we start at C. We need to go backwards, right? So we're going to subtract there. Does that do it? Right. So if we say we're in row 0, and we're starting here, where the cursor is here, where the mouse is, that's going to be column 3, and then we want to go down a row to row 1, but we want this one, so that's 3, so that's 3 minus 1, so this, whatever C is, I want C minus 1, C minus 2, C minus 3. That should do it. All right, let's see it. This is I think this is done completely. Let's check it. So pick a column. We want to check the diagonals. I might get it. Oops, I lost. I wasn't paying attention. let me try this one. Well, I better take that one there. And I'm going to try to get a diagonal here. Zero, 1, 2, 3, right? That's the one I want to get. So I just want O to play there. I'm going to get it. 0, 1, 2. There it is. I got the diagonal there. Player wins. That's a left sloping diagonal. Anyway, that's it. You know, we did it. We did the whole thing. And you see how we did it incrementally, breaking it into functions, using stubs, testing a piece of functionality at a time until we converge to the final solution. The other thing that you might have learned through this process is how to model something on the outside with a data structure. And what we used a two-dimensional array to represent this board. So you got to have a data structure. You need data, because the programs need data to work on. So it's just picking the right representation of information for your problem is a big part of the problem, big part of the solution. And then devising the algorithms to operate with that data structure. That's like, in a way, the second half of the solution. So that's it for that problem. Is there anything else? How are you doing with the tic-tac-toe? You see the similarities on how to solve that problem? That's a really good problem to work on. Yeah. And games, you know, a lot of programmers learn programming by writing games. You know, so I think most programmers like games, and they dream about writing video games. Now, almost all of them, like 99% of them. And it's fun because games are fun, and so they like to code up games, and that's a great way to learn. You get sucked in, you get working with a hard problem, you start practicing that way. And then when you get older, then you get a job, and now you're not programming a game anymore. You're doing something else, right? Like financial transactions or DNA analysis, you know, rocket projector, whatever it is. All these different problems you can work on. Website development, you know, lots of different. There's so much computer programming that's happening in industry. It's just everywhere, and it's easy, relatively easy to find work if you're good at this. You're almost guaranteed. If you're bad at it, you graduate with a degree and you're bad at this, you still have a shot at finding work. But if you're good at this, you have no trouble at all finding a nice job. I mean, a well-paying job right off the bat when you graduate. That's what I observed, you know, over the years. Even when the economy has been horrible, you know, the students that have graduated that have really learned how to code have been able to find work, and well-paying work. Anyway, that's, but you don't want to do it just for that. You want to do it because it's fun and you enjoy it and it's satisfying. Otherwise, it's going to be, you know, horrible. So don't do it if you don't love it. Any questions about the final? I mean, it's simple. There's nothing else I could say, really, except to repeat things that I've said in the past. Everyone ready? Okay. Oh, one question back there.
What time does the final start?
It starts at 12 o'clock in this room on Wednesday. And it goes for an hour and 50 minutes, 2 hours.
2 hours?
Yes, 2 hours. Okay. All right, good. See you Wednesday.